be soon flying around in the U.S. orbital segment of the space station, helping astronauts out, doing some routine chores for them, and also doing more research and science as a microgravity test bed, replacing the sphere's test bed. Part of what we want to do on orbit is understand better how astronauts and robots can interact. But it also can be used as a tool by ground controllers. So we can use the camera to do video surveys or to observe crew activities so that the ground can be actually ready to answer any question the crew might have in a complex activity. For future missions, absolutely, those sorts of tasks can be taken over by a robot. We expect to have these sort of robotic helpers. So we will have 3 in orbit eventually. So 2 are launching on NG-11, and then the third one will be joining it later this summer.
We live an exciting time where the lift capacity to low Earth orbit becomes amazingly affordable. The interesting feature of specialty optical fiber for the space economy is that optical fibers have unique value to mass ratio. Just to give you an example, specialty fiber preform should be able to produce multiple kilometers, let's assume 40 kilometers of optical fiber. That brings the value of optical fiber to millions per kilogram, while the lift price for optical fiber is in tens of thousands of dollars. So we see an interesting opportunity to commercially utilize International Space Station for sustainable manufacturing.
The Virginia Space ThinSat program is at its heart a STEM outreach program. So we are currently active in over 11 states with over 50 schools. We're launching 63 satellites. So we are actually on the avionics ring, which is the part that's just underneath Cygnus. So we are what's considered a secondary payload. The Cygnus goes to the space station, we do not. We deploy just below the space station. What Bob has here is the ThinSat. So this is what the students are working on and building. So the students can design whatever can fit in that space.
Think of what that's going to do for the space industry. If you can start a kid with his own satellite that had a sensor in it up in space when he's in elementary school, and he does it in junior high, and he does it in high school, and he does it in the university, boy, you're going to have some good products out of it. So doing something like this at a cost that you could get down into the elementary schools, and we do have ThinSat projects in the elementary schools, I think it's really great.
So this project is actually 7 years in development. Nina and I have both spent basically all of our adult science careers preparing for this. What antibodies are they are proteins produced by B cells, and they are a type of white blood cell, and it's important for fighting infection. And the antibody repertoire is then that collection of antibodies that you have. So our project is looking specifically at the anti-tetanus toxoid repertoire. Obviously, our ideal response here would be that our mice would not have any difference between our ground mice and our space mice. And this would be able to tell us that hopefully our astronauts will be protected in space. But what we're really expecting to see is that there's going to be some form of immune dysregulation.
Mike and I have actually been working down at Kennedy Space Center in Florida for the past few weeks, vaccinating our mice here on the ground before we send them to space. So after we send them to space, they will acclimate to the new environment, and then we'll challenge them again with the same vaccine again. After that, we'll allow the immune response to develop, because it takes some time, and then the astronauts will collect tissue samples for us and send it back down to Earth so we can do the data analysis. But I think the coolest part of this experiment is that while the astronauts are up in space doing these experiments, we're here down on the ground doing the exact same things that they're doing. And yeah, that's how we get some really powerful science.